Welcome to Science After Dark. Today's episode asks whether the three-dimensional space around us is truly fundamental, or whether everything within it could have an equivalent description written on a lower dimensional boundary.
It is a deeply profound question, and it really begins with just observing the physical space you are in right now.
Exactly. I want you to just take a slow, quiet breath and look around the room you are currently resting in. Pick an object, any object. Maybe it is a lamp on your nightstand or a chair in the corner or even just the device you are using to listen to us right now.
Notice the dimensions of that object. It has height, it has width, and it has depth.
Right. And if you were to reach out in the dark and touch it, your hand would move through a solid, measurable, three-dimensional space to get there. It is, the most undeniably real, visceral experience we have as humans. We feel very secure in the knowledge that we exist inside a 3D container.
We do, yes. It is the absolute bedrock of human intuition. Our brains, they evolved specifically to process a physical reality defined by those three spatial dimensions: up and down, left and right, forward and backward.
But tonight, we are going to explore a very different kind of reality. What if everything you just envisioned, the lamp, the chair, the room, even the hand you reached out with, what if none of that 3D volume is actually fundamental?
That is a staggering thought to sit with. Are you saying that the depth we perceive is, well, fundamentally no different than the depth you might see on a flat screen?
Essentially, yes. A highly convincing playback, cast by a dense network of data living on a distant, impossibly flat, two-dimensional boundary. When you first hear that, I know it sounds like an abstract philosophy debate or perhaps the premise of a quiet science fiction story.
It really does sound like fiction, at first glance.
But the fascinating part is this is not science fiction. This is what physicists call the holographic principle. It is a serious, mathematically rigorous framework that emerged from some of the most complex physics of the last 50 years.
And our mission for this deep dive is to gently unpack this concept. We want to explore the history, the quiet theoretical breakthroughs, and the math to understand if this three-dimensional space is, in a sense, an illusion.
To do that, to really understand how the entire universe could be a hologram, we actually have to begin far away from here. We have to start by looking at the most extreme, silent, rule-breaking objects in the cosmos. We have to talk about black holes.
Which makes perfect sense, because black holes are the ultimate laboratory for this kind of physics. They are places where our standard models are pushed to their absolute breaking point.
Right. When gravity becomes that intensely strong, the normal, comforting rules of reality just stop working. And that forces physicists to ask questions that simply wouldn't make sense anywhere else in the universe.
And there's one specific question I recall that really kicked off this whole journey. It was asked in the early 1970s by a physicist named Jacob Bekenstein.
Yes, Bekenstein. He was staring down a theoretical problem that was, quietly but surely, breaking the laws of physics. It is known as the information paradox. To visualize this, let's imagine you have a physical book in your hands.
Okay, a book.
This book contains unique information. The words on the pages, the ink, the exact microscopic arrangement of carbon and oxygen atoms that makes this specific book perfectly unique in the universe. Bekenstein asked a very simple, very dangerous question. What happens to that unique physical information if you drop the book into a black hole?
I see why that would cause a panic in the physics community, because if we look at the bedrock rules of quantum mechanics, information is never supposed to just vanish.
Exactly. The laws of quantum mechanics are built strictly on reversibility. If you were to take that same book and, say, burn it in a fireplace, the information isn't actually gone. It feels gone to us, but it isn't.
Right, because if you had a supercomputer powerful enough to track every single photon of light radiating from the fire, every wisp of smoke drifting up the chimney, and every speck of ash left behind, you could theoretically run the clock backward and reconstruct the book perfectly.
You could, but a black hole is a completely different beast. Its gravitational pull is so intense that nothing, not even light, can escape the event horizon. If our book crosses that dark boundary, it seems like the information is simply, well, gone from the universe.
And it gets even more complicated when you factor in Stephen Hawking's work, doesn't it?
It does. Hawking later proved that black holes are not completely black. They slowly leak a very faint Hawking radiation, and over trillions of years, they eventually evaporate into nothingness.
But that radiation is totally random, right? It doesn't carry the book's information back out into the universe.
That is the core of the paradox. The book goes in, the black hole eventually evaporates, and the information is just deleted. which violently breaks the laws of physics.
It breaks the second law of thermodynamics, to be precise. That law states that the entropy, or the total disorder and hidden information of a closed system, must always increase.
Exactly. If you can just throw a highly complex, high-entropy object like a book into a black hole and make it disappear forever, then the total entropy of the universe goes down. And the universe simply does not allow that.
So how did Bekenstein resolve this? How do you balance the universal ledger?
Well, to fix this crisis, Bekenstein proposed that the black hole itself must have its own entropy. The inversion of the book isn't destroyed, it is stored in the black hole itself. But this is where the mathematics get deeply counterintuitive.
How so?
Think about packing a room. Normally, if you're packing a room full of furniture, the amount of stuff you can fit inside depends entirely on the room's volume, right? The bigger the 3D space, the more couches and tables you can carefully arrange inside it.
That is just common sense. Volume dictates capacity.
But Bekenstein, and then Hawking, proved that a black hole does not work that way. A black hole's entropy, its hidden information capacity, is not proportional to its volume at all. It is proportional to the surface area of its event horizon.
Wait, the surface area?
Yes, the two-dimensional skin of the black hole. The storage capacity of this cosmic trash can is determined solely by the area of its boundary. Specifically, they found it maxes out at 1 bit of information for every 4 Planck areas on that surface.
A Planck area, just to clarify for a quiet reflection here, is based on the Planck length. That is the smallest measurable unit of distance in physics.
Right. It is roughly 10 to the minus 33 centimeters. A scale so infinitesimally small, it is almost impossible for the human mind to picture.
So imagine a microscopic grid drawn delicately on the dark surface of the black hole, where every little square is 1 Planck length by 1 Planck length. The math dictates that each of those minuscule squares can hold exactly 1 bit of data.
Exactly. But bringing it back to the room analogy, it is like saying the maximum amount of furniture I can put into a room is completely determined by how much wallpaper I can stick to the walls, completely ignoring all the empty 3D space in the middle of the room.
I can see why the physics community would push back against that in the 1970s. How does that make any physical sense? The volume inside a black hole is massive.
It feels wrong because we, as physical beings, assume volume is the primary container of reality. But mathematically, this area law tells us that the interior volume of a black hole is entirely redundant.
Redundant?
Everything you could possibly ever need to know about what fell inside that black hole.
Yeah.
Every book, every speck of dust, every collapsing star is perfectly and completely encoded on the two-dimensional skin of the horizon.
So the 3D interior is, in a way, just a projection of that 2D surface.
Precisely. If the maximum amount of information a region of space can contain is capped by the area of its boundary, it implies that space itself works entirely differently than our brains perceive it. The 3D volume simply doesn't hold any more data than the 2D surface wrapping around it.
That is a staggering realization, but for a long time, maybe 20 years or so, physicists just treated this as a weird, isolated quirk of black holes, didn't they?
They did. The universe is weird, black holes are weirder, end of story.
Huh?
It was tucked away as a quiet anomaly. But then, in 1993, things expanded dramatically. A Dutch physicist named Gerard Hooft looked at this quirk and asked a massive, beautiful question.
What did he ask?
He asked, what if this area law applies to all of space? He realized that if you take quantum gravity seriously, this cannot just be a special rule for black holes. Black holes are just the most extreme packing of matter.
So he suggested that the true physical description of what happens inside any volume of space, even the quiet room you're resting in right now, can be fully described by a theory operating exclusively on its boundary.
Yes. And then, a couple of years later, in 1995, Leonard Susskind pushes this even further. He integrates Hooft's proposal with string theory and publishes a paper arguing this is a fundamental limit on reality itself. He famously calls it, "The world is a hologram."
I want to pause on that word holographic. Because when people hear that the universe is a hologram, they often picture a glitchy, translucent projection from a sci-fi film.
Right, a glowing blue grid flickering in the dark.
Is this just poetic language Susskind is using, or is it a literal mechanism?
It is a literal mathematical mechanism. To understand it, think about how a physical holographic plate works in a dark laboratory. You have a flat, two-dimensional piece of film.
Okay, a flat film.
If you just look at the film under normal room light, it looks like a chaotic mess, just static and swirls. There's absolutely no depth to it. But when you shine a very specific, pure laser through that flat film, that encoded 2D data projects a fully three-dimensional image into the air.
And it is a true 3D image, right? You can walk around it, and as you move your head, the perspective gently changes. You experience parallax.
You experience depth, yes. But the depth doesn't actually exist in the film. The depth is a highly convincing illusion, created by the flat, two-dimensional data.
And Hooft and Susskind proposed that our universe operates exactly like that laboratory plate.
They did. They proposed that the deepest, most fundamental physics of our reality, the static on the film, so to speak, lives entirely on a lower dimensional boundary. The three-dimensional world we experience with our senses, the gravity that holds us to the bed, all of it is just what that boundary data looks like when it's mathematically played back.
It is a beautiful concept. It solves the information paradox so elegantly. But in theoretical physics, a beautiful idea isn't enough. You need the math to back it up.
You do. And for a few years, this holographic principle was just an abstract, elegant conjecture. But then, in 1997, a physicist named Juan Maldacena published a paper that completely shook the foundations of the physics world.
It is hard to overstate Maldacena's impact. Until that paper, physicists were just quietly debating whether this hologram idea was even mathematically possible. Maldacena didn't just argue for it, he actually built one.
He found the first explicit, mathematically precise proof of the holographic principle in action. It is known as the AD-SCFT Correspondence. And I want to take this slowly because the mechanics here are wonderfully strange.
Let's unpack it. What does AD-S stand for?
AD-S stands for anti-de space. This is a very specific kind of mathematical spacetime. It has what we call a negative curvature. The easiest way to visualize it in your mind is to picture the shape of a saddle or maybe a curved potato chip, but stretching out infinitely in all directions.
Okay, I can picture that gentle, sweeping saddle curve.
We call this 3D interior space the bulk. And crucially, the bulk has gravity in it. But because of how this saddle shape curves, if you travel infinitely far outward, you eventually hit a solid mathematical boundary, a flat 2D wall wrapping around infinity.
So that is the bulk, and its distant flat wall. Now, what happens on that boundary? What does the CFT stand for?
That is the conformal field theory. This is the physics that lives exclusively on that flat 2D boundary. And the most important part of Maldacena's discovery is this. There is absolutely no gravity in the conformal field theory.
None at all.
None. It is just standard quantum mechanics. It is very similar to the math that describes how subatomic particles interact in a flat space, completely and utterly devoid of gravitational forces.
So we have two completely different worlds here. The bulk, which has depth, extra dimensions, string theory, and gravity, and the boundary, which is flat, lower dimensional, and has zero gravity.
Right, and here's the part that is so profoundly beautiful. Maldacena showed that the physics in the saddle-shaped bulk, with its gravity, is mathematically identical to the quantum physics on the flat boundary, without gravity.
They are mathematically identical, but they look completely different.
They do. It is like having two completely different languages describing the exact same reality.
Like a language dictionary. That is a perfect way to visualize it. Maldacena proved they are dualities.
Exactly. If you are a physicist, sitting in a quiet office, struggling with a ridiculously complex equation about gravity and black holes inside the bulk, you can run it through Maldacena's dictionary.
And it translates that heavy gravity problem into a much simpler quantum particle problem on the boundary. You solve the math on the flat boundary, run the answer back through the dictionary, and you get the exact right answer for the gravity problem in the bulk.
It gives me chills every time I think about it. They aren't just similar theories that happen to rhyme. They are literally the exact same physics, wearing two completely different mathematical masks.
And that is why it was so revolutionary. Unifying the math of quantum mechanics with the math of gravity has been the ultimate, quiet, holy grail of physics for nearly a century. They famously refused to work together.
But Maldacena found a back door. He achieved, essentially, quantum gravity without gravity. His math suggests a truly radical idea, that maybe gravity isn't a fundamental force of nature at all.
If the physics of the bulk perfectly match the physics of the boundary, and the boundary doesn't have gravity, it implies that gravity and the extra dimension of space it operates in are emergent.
Emergent space-time. They are just what quantum mechanics looks like when viewed from a different perspective. But this realization begs a massive lingering question.
Which is?
If gravity isn't fundamental, and the actual depth of space we move our hands through isn't fundamental, then what exactly is space made of? If it is not just an empty, dark state, what is stitching the fabric of the universe together?
Well, if space is essentially a playback of data, you have to look at how that data is structured on the boundary, right?
Yes. And that leads us to the fascinating work of physicists like Brian Swingle. He started looking at this at CFT correspondence using a mathematical tool called tensor networks.
How would you describe a tensor network to someone resting with their eyes closed?
From a mathematical standpoint, it is essentially a complex, delicate scaffolding. It is a way of tracking exactly how individual quantum data points connect and relate to each other on that boundary.
Okay, a scaffolding of connections.
Swingle found something extraordinary. He found that the geometry of the bulk, the actual physical distance between two objects in the 3D space, is directly dictated by the amount of quantum entanglement on the boundary.
Quantum entanglement. Let's define that softly, just to be clear. Entanglement is the phenomenon where two particles become inextricably linked.
Right. The state of one particle instantly correlates with the state of the other, even if they are light years apart in the dark. It is a pure, invisible information connection.
And Swingle's work suggests that this pure information connection is what actually creates the illusion of distance.
Exactly. The more entangled two regions on the flat boundary are, the physically closer together they appear to be inside the 3D bulk space. Physical space is basically a quilt, stitched together by invisible threads of quantum entanglement.
Which leads to a very natural but slightly unsettling question. What happens if you take a mathematical pair of scissors to those threads?
What if we sever the entanglement?
Yes. What happens to the space?
The math provides a terrifyingly clear, precise prediction. If you cut the entanglement between the particles on the boundary down to zero, the 3D bulk spacetime literally tears apart.
The space just rips.
It violently, quietly disconnects. The spatial distance between points inside the bulk suddenly becomes infinite. You would end up with two completely disconnected, drifting universes.
That is a profound realization. It proves that space cannot just be a void where things happen to exist. The connectivity of reality itself fundamentally relies on quantum entanglement.
Without entanglement, there is no space. Space is an emergent property built entirely out of quantum information.
It is a beautiful picture of the universe, but it also sounds terrifyingly close to mysticism if we aren't careful. I think we need to step back gently and separate established fact from theoretical speculation.
I agree completely. Physics isn't about feelings or aesthetic beauty. It is about what can be rigorously proven. We have to be very careful not to overstate what has actually been proven about our specific, real universe.
So let's ground this. Based on the physics we actually have today, are you and I and the bed we are resting on literally flat data projections? Are we living in a hologram right now?
To answer that honestly, we have to gently separate the science into three distinct tiers of certainty.
Okay, let's hear them. What is tier 1?
Tier 1 is solid fact. This brings us back to Beakenstein and Hawking's work from the 1970s. The fact that a black hole's entropy, its hidden information capacity, is tied directly to its surface area and not its volume.
That is on incredibly solid ground, yes.
It is as thoroughly established as anything in theoretical physics gets, without us physically flying a probe into an event horizon. The cosmic trash can absolutely has a strict data limit, and it is written on its skin.
So tier 1 is fact. Black holes are undeniably holographic. What about tier 2?
Tier 2 is rigorous math. This is Maldaceni's ADIA CFT correspondence. The holographic principle works perfectly as a mathematical translation. The equations are flawless, they've been cross-checked for decades, and they're used by physicists every single day to solve real problems.
But there is a catch with tier 2, isn't there?
A rather significant catch, yes. AD-SCFT only works perfectly in anti-de Sitter space. It strictly requires that saddle-shaped, negatively curved universe to function.
And if we open our eyes and point our telescopes at the night sky, our actual universe does not look like a saddle.
No, it doesn't. As best as we can measure, our universe has a positive cosmological constant. It is expanding outward in all directions. We live in what is mathematically called de Sitter space, not anti-de Sitter space.
Ah, I see. So the dictionary works perfectly, but it translates a language spoken in a universe shaped completely differently than the one we actually inhabit.
Precisely. Which brings us softly to tier 3, active conjecture. How do we take this flawless, beautiful math and apply it to our messy, expanding, positive curvature reality?
I recall the work of physicist Raphael Bousso in 1999 being crucial here. He developed something called the covariant entropy bound.
Yes. Bousso's work is a monumental step toward making this real for us. He figured out a precise mathematical recipe for calculating how much information can pass through surfaces in realistic, expanding cosmological settings.
So he basically figured out how to gently draw the boundary in a universe exactly like ours.
He did. He proved that the strict data limit still holds true, even without the neat, saddle-shaped infinite walls of Maldaceno's math.
But even with Busso proving that the data limit exists here in our room, the deepest claim, the idea that our actual physical bodies, our planet, our quiet nights, are literally being projected from a lower dimensional surface.
That remains unproven. It is a highly respected conjecture. A massive portion of the physics community takes it extremely seriously because the math consistently points in that direction. But it has not been experimentally confirmed.
We are still quietly debating whether the holographic principle is just a spectacularly useful mathematical mirror for solving tough equations, or if it is the literal physical reality of our existence.
We don't have the final answer yet. But what does this all mean for us? Even if we aren't literally flat, even if we are flesh and blood 3D beings, we still have to accept a radical shift in how reality works.
Reality has a built-in data limit.
It does. If you try to cram too much information into a quiet region of space, the universe literally cannot handle it, and it gracefully collapses that space to a black hole. The universe has a storage capacity, and that capacity is engraved on the area of its skin, not the volume of its space.
It completely dismantles the classical view of reality. The idea that space is just an empty, dark box where particles bump into each other is gone. Space and information are inextricably fundamentally linked.
It really is a total paradigm shift, and it perfectly frames why physicists are so deeply obsessed with this. The century-old hunt for a unified theory of quantum gravity isn't going to be found by looking closer at 3D particles.
The ultimate theory of reality is going to be a theory of information. Data processing encoded on boundaries, creating the illusion of a reality with depth.
Exactly. So the next time you are lying in the dark, looking out into the empty space of your room, I want you to remember that its true capacity might just be written quietly on the walls. Which leaves me with one final lingering question. Something for you to mull over as you drift off.
What is the question?
We talked earlier about the flat holographic plate and how it needs a physical laser shown through it to project the 3D reality we can actually see and interact with. Well, if the 3D reality we experience every single day is truly just a playback, a projection of quantum data encoded on some distant 2D surface, what exactly is acting as the laser? If the universe is fundamentally made of information, who or what is reading the data? This has been Science After Dark. Rest well and let the questions continue in the background.